Hello, my name is Scott Simpson, and today we'll be talking about phase diagrams associated with binary solutions. The two phases that we're mainly going to concern ourselves with are liquid and gases, so we're going to assume we have a liquid-liquid mixture in this case. The word binary, of course, means two components. So what we're going to do is consider an ideal system. So let's consider an ideal system. Given that we have an ideal system, meaning an ideal gas, ideal liquid, what we're going to explore is utilizing Raoult's law to figure out the pressure of both the liquid and the gas, and when we have a mixture. We're then going to extend this to a phase diagram, so a picture to really explain what's going on in this solution. So given that we are considering an ideal system, the vapor pressure of each of our species, we're going to call one A and one B. For each liquid, the mixture is given by good old Raoult's law. Oops, forgot an A. Where? We have the pressure of A in our system is equal to the mole fraction of A times the pressure of pure A. So those stars, that means pure A. And we also have the other secondary component, B. Ooh. So again, let's describe what these things are. Let's just look at this one for now. This P right here, that's the pressure of A at whatever mixture we have. So vapor pressure in mixture. That's the mole fraction within the mixture. And this P star, remember, star means pure system. So this is the pressure, vapor pressure, excuse me, of pure A. The same is true for B. The other thing we know is since this is a binary mixture, the following expression must be true. If you have only A or B in your system, when you add up their mole fractions, it should total to be 1. Okay, so let's look at an example where we're utilizing these equations. We're going to have a mixture of methylbenzene and benzene. We are told what the total pressure is, and we have to try and figure out what is the mole fraction of those constituents. All right. So example, determine the mole fraction of each component of a liquid mixture of benzene and methylbenzene. That has a vapor pressure of 62.5 torr. Assume ideal behavior. Okay, so we're trying to figure out the volume of our, or excuse me, the vapor pressure. We have the vapor pressure of our solution, of our mixture, and we want to try and figure out the mole fractions. So we know the total pressure has to be equal to the vapor pressure of benzene. We're just going to shorten that to B while it's mixed, plus the pressure of methylbenzene. We're going to switch that to M. Okay. However, we don't know these pressures. If we knew that, this would be way easier. We do know the total pressure here. However, utilizing Raoult's law, we can break these down further. We could look at the mole fraction of benzene times the vapor pressure of pure benzene plus the mole fraction of methylbenzene times the vapor pressure of pure methylbenzene. We can find those pretty easy. You can look those up in a table. For the temperature I went with, which I think was 20 degrees C, the vapor pressure of pure benzene was equal to 75 torr. And the vapor pressure of pure methylbenzene was 25 torr. Oh, I'm sorry, it was 21 torr. Okay. Something else we do know from this equation is we know the mole fraction of benzene plus the mole fraction of methylbenzene is equal to 1. So if we know one, we know the other. If we manipulate this around, let's solve for the mole fraction of methylbenzene. That would just be 1 minus the mole fraction of benzene. What we're going to do now is take this in, plug that into here. And now, instead of having one equation and two unknowns, we now have one equation, one unknown. It's solvable. So we have P total is equal to the mole fraction of benzene times that of pure benzene plus 1 minus the mole fraction of benzene times that of pure methylbenzene. We can plug in some numbers here. Note the numbers in all cases have the units of torr, except for these numbers here. I'm going to leave that off and just toss it in at the end. So we know our total pressure is 62.5. Our pure pressure of benzene was 75 torr. And then we have chi x plus 1 times chi b times 21. We can manipulate that further. 62.5, 75 chi benzene plus 21 minus 21 chi of benzene. We can solve this further. Let's slap this and this together and then move the thing over to the other side. So we should end up with 41.5 is equal to, basic math, go 54 chi b. We manipulate that further. Chi of b should be equal to 0.76.9. So we know the mole fraction of benzene. Now all we have to do is just plug in here to get our mole fraction of methylbenzene. We do that and we end up with 0.231. Okay, so we can utilize Raoult's law to figure out those pressures. However, I said we were going to look at a phase diagram. Let's try to draw a phase diagram out. It won't be for this exact same situation, but we'll still utilize important information from it. So we're going to take some time and draw that out. But it's going to operate under similar principles where we're keeping track of a binary mixture We may know the vapor pressure of the liquid, and we can figure out the composition of not only the liquid, but also the gas. So the diagrams. I'm going to try my best to draw a plot. Hopefully it comes up well. Generally, we have pressure on the x-axis, or excuse me, y-axis. And remember, we're talking about a two-component mixture. We'll have component A and component B. And along here, we have the mole fraction of A. The maximum that we can have is all pure A, or we can have all pure B. Okay, so we're going to try to mark those points here. This is where we would have PB star, and let's say up here, that's where we would have PA star. So the pressure, or the vapor pressure of pure A and the vapor pressure of pure B. What we're going to do next is draw the liquid line. Hopefully I pick a good point after that. And then I'll have the vapor line. Okay, and we're going to have two specific points we're going to consider. We're going to have point A, and then directly across, if we cut across to the vapor line, we'll have point B. Okay, so utilizing this, if we knew the vapor pressure of our mixture, let's say it was at point A, we'd be able to know the pressure of our vapor. And from that, we'll be able to know how much vapor, or the mole fraction of the gas above the liquid, how much of it is A. And then if we have another, if we consider the mole fraction in the liquid, we'll know that too. So all we have to do is drop down to this point, and that is the mole fraction of A in the liquid. This point directly from B. That would be the mole fraction of A in the gas phase. So we can utilize this binary phase diagram to figure out those mole fractions and any pressure we're really interested in. So with that, I would like to thank you for watching. And if you have any questions or comments, please leave them below. Thank you.